Class. A class is the basic blueprint of object-oriented programming. It defines what something should look like and what it should be able to do, but it is not the actual thing itself. You can think of it like the design of a house. The blueprint describes the number of rooms, the doors, and the windows, but nobody can live inside a blueprint. In programming, a class describes the properties, called attributes, and the actions, called methods, that an object will have. For example, a car class might define a color, a model, and a speed, along with actions like start, stop, or accelerate. The class simply provides the structure. It does not represent a real car until an object is created from it. This separation between the design and the actual instance makes programs easier to organize, reuse, and expand as projects become more complex. Object. An object is the real instance created from a class. If a class is the blueprint, an object is the finished house built from that design. Multiple objects can be created from the same class, and each one can have different values while still sharing the same overall structure. Imagine a student class with properties like name, age, and grade. One object could represent Emma, another could represent David, and another could represent Sophia. They all belong to the same class, but each stores its own unique information. Objects also perform actions through the methods defined by their class. A car object can start its engine, a bank account object can calculate its balance, and a shopping cart object can add products. Almost everything in object-oriented programming revolves around creating and managing objects because they represent the real data that a program works with. Encapsulation. Encapsulation is the practice of keeping data and the methods that work with that data together while protecting important information from unwanted access. Instead of allowing every part of a program to change values directly, the class controls how those values can be viewed or modified. Imagine a locked box that stores valuable items. People cannot simply reach inside whenever they want. They must use the proper key or follow approved rules. In programming, this often means making variables private and allowing access only through carefully designed methods. For example, a bank account should not allow anyone to directly change the account balance. Instead, users deposit or withdraw money through specific functions that verify whether the operation is valid. Encapsulation helps prevent accidental errors, protect sensitive data, and make software more reliable because every change follows controlled rules. Abstraction. Abstraction focuses on showing only the information that users need, while hiding unnecessary implementation details. Every day, people interact with complex systems without understanding everything happening behind the scenes. Pressing the power button on a television turns it on, even though most users have no idea how electricity flows through its circuits. Programming follows the same idea. A developer may use a function without knowing every line of code inside it. The internal complexity remains hidden, while the useful behavior stays visible. This allows programmers to focus on solving problems instead of constantly thinking about low-level details. As software grows larger, abstraction becomes increasingly valuable because different parts of a system can be developed, improved, or replaced without affecting how people use them. It creates cleaner code and makes complicated applications much easier to understand and maintain. Inheritance. Inheritance allows one class to build upon another by reusing its existing features instead of starting from scratch. This relationship is often compared to a family tree, where children inherit characteristics from their parents while also developing unique traits of their own. In programming, a vehicle class may define common features such as wheels, speed, and braking. A car class can inherit those features and then introduce additional capabilities like air conditioning or navigation. A motorcycle class can inherit the same basic structure while adding features specific to motorcycles. This approach avoids repeating identical code in multiple places. When the parent class is updated, the improvements automatically benefit the child classes as well. Inheritance creates organized hierarchies, encourages code reuse, and simplifies the development of large systems where many objects share common behavior but still require their own specialized functions. Polymorphism. Polymorphism allows one interface or method name to produce different behavior depending on the object using it. Although the same instruction is given, each object responds in its own appropriate way. Imagine asking different musical instruments to play the same note. A piano, a guitar, and a violin all receive the same request, but each produces a unique sound. Programming follows this same principle. A method named draw could display a circle, a rectangle, or a triangle depending on which object calls it. Likewise, an animal's speak method could return a bark for a dog, a meow for a cat, or a chirp for a bird. The code using these objects does not need separate instructions for every possible type. Polymorphism improves flexibility, reduces repetitive code, and makes programs easier to extend because new object types can fit naturally into existing systems. Constructor. A constructor is a special method that automatically runs when a new object is created. Its main purpose is to prepare the object so it starts in a valid and usable state. Think of launching a rocket. Before liftoff, every system must be checked, fuel must be loaded, and all settings must be configured. A constructor performs similar preparation for an object. When a person object is created, the constructor might assign the person's name and age immediately. When creating a database connection, the constructor may establish communication with the server before any data is requested. Without constructors, programmers would have to remember to initialize every object manually, increasing the chance of mistakes. Constructors ensure consistency by giving every new object the correct starting values from the moment it exists. Access specifiers. Access specifiers define who is allowed to use different parts of a class. They create boundaries that protect important data while exposing only what other parts of a program should interact with. The most common access levels are public, private, and protected. Public members are available to everyone. Private members are restricted to the class itself, preventing outside code from changing them directly. Protected members are available within the class and its inherited subclasses, providing controlled access for related classes. This system works much like different security levels inside a building, where some rooms are open to visitors, others are reserved for employees, and a few are accessible only to management. Access specifiers improve software security, reduce unintended changes, and encourage developers to interact with classes through well-designed interfaces instead of manipulating internal details directly. Message passing. Message passing is the way objects communicate with one another by requesting actions or exchanging information. Rather than reaching directly into an object's internal data, one object sends a request and waits for the receiving object to respond. This is similar to sending a message through a chat application. You ask a question, and the other person decides how to answer based on the request. In object-oriented programming, a shopping cart object might send a request to a payment object to process a transaction. A user object could ask a database object to retrieve account information. Each object focuses on its own responsibility while cooperating with others through clearly defined methods. This communication style keeps systems organized, reduces unnecessary dependencies, and allows different components to work together without exposing their internal implementation. Relationships. Relationships describe how different classes and objects connect and interact within a program. Not every object exists independently. Many rely on other objects to perform meaningful tasks. Some relationships represent ownership, where one object completely contains another, such as a house containing rooms. Others represent association, where two objects cooperate without depending entirely on each other, like a teacher interacting with students. Aggregation describes a weaker ownership, where objects can exist separately, while composition represents stronger ownership, where one object's lifetime depends on another. Understanding these relationships help developers model real-world systems more accurately. Instead of treating every object as isolated, object-oriented programming builds networks of connected components that cooperate to solve larger problems. Well-designed relationships make software easier to maintain, easier to expand, and better suited for handling complex applications over time.